You might have seen in the news last few days of the past week, and now on Saturday that a rocket was launched from Florida into space with 2 astronauts on board, and they just docked with the International Space Station. Now that we have momentum, we can talk about how it is that a rocket in outer space is capable of accelerating. Because really, if a rocket accelerates, it's because there was a force on it. But what's around to push on a rocket in outer space? And the answer is nothing. And that's how it works. Let's talk about a rocket with some fuel on board with total mass m. As it burns and exhausts the fuel, the mass on board the rocket decreases. So dm dt is negative. Now dt is always we're going to let time run forward. Backwards running time is weird. Let's not deal with like Hitchhiker's Guide to the Galaxy kind of spaceships. This is, this is real. Time runs forward, so we can multiply both sides. That means dm must be negative. So the small differential change in the mass of the rocket, dm, is negative, which makes sense. The mass of the rocket is decreasing. Okay. Since we're in outer space, the net external force on the rocket and its fuel is 0. Which a couple segments ago, I said meant that the momentum beforehand should be equal to the momentum afterwards, after some event. And let's say that that event is the expulsion of exhausted fuel. Before we do that, we have a rocket with some mass that is traveling through space at some initial velocity v. Well, just before this exhausting happens, there is some velocity, let's call it v. Afterwards, there are 2 pieces in the system. Now, I mean, before, I guess there were 2 before. It was the rocket and then the quantity of fuel that we were about to exhaust. But it was all on board the rocket, so it's all wrapped up in this one term. Now that we've expelled some fuel, now there is fuel over here and the rocket with the rest of its fuel over here. So we've got 2 things in the system now, 2 different objects that we need to include to talk about the total momentum of the rocket fuel system after we exhaust. Okay. The mass of the rocket, and I'm going to go pretty slow here, the mass of the rocket and the new velocity of the rocket, plus the mass of the fuel and the new velocity of the fuel. The spent fuel, the exhausted fuel. mv. equals. Now, the mass of the rocket has decreased a little bit. By how much? dm. I'm going to write it this way because remember, dm is intrinsically negative. So m plus dm, m plus a little decrease, gets us a lesser mass than we started with. Our velocity is whatever it was plus a bit. I've got these vectors, well, let's leave them for now. The fuel was originally on board the rocket and was included with this mass m. Now it's not on board the rocket, so the rocket's mass has decreased, which means the amount by which it has decreased is the amount of mass of fuel we just expelled. So the mass of the fuel is that amount, dm. But dm is negative. So I can't say that there's a mass of fuel dm. A negative mass of fuel doesn't make any sense. A negative change, okay, but a negative, like the amount by which it has changed is the mass of the fuel. It just has to be, I mean, mass is a positive quantity. So I have to write negative dm as the mass of the fuel. Dm is negative, so putting the minus sign lets me talk about a positive fuel mass. Its velocity, as we are watching the whole thing go by, the fuel that gets pushed out the back is all still moving probably to the right as we're standing here on our asteroid watching this go by. This fuel was pushed that way some speed according to how the rocket exhausts its fuel, but that's a leftward going velocity that needs to be added to the fact that the whole thing was already moving with velocity v. This minus sign is directional. And we're talking about a one-dimensional problem. So now that we've handled the direction here, I'm going to work my way backwards and just get rid of it was going to the right. I assume that it's going to the right with a little bit extra velocity now. This was a rightward, this is leftward. Okay. That's the setup. Let's chase through some consequences. MV equals, let's FOIL MV plus MdV plus VdM plus dm dv plus negative v dm the minus gets us a plus v exhaust dm. I've got an MV on both sides. Subtract. We've got a minus VDM and a plus VDM. So those will cancel on their own. And then there's a 0 here. We can move one of these over here. M dV is equal to negative V exhaust dm. I guess there's this term to worry about. But here's the thing. These are dV and dm, not delta. This isn't some macroscopic change in mass. It's so small that it's almost immeasurable. Well, I mean, we're talking calculus sizes here, right? These are differential changes in mass and velocity. I think you can maybe see we're setting ourselves up to integrate. Anyway, so like we're talking about super small changes in mass and velocity, super small, and then we're going to multiply them together. The order of magnitude of this term is so small. I mean, it's like less than it's so small. It's less than infinitesimal. It's infinitesimal squared, which is like gone. It's like, we don't care. It's gone. It's so small we can ignore it. So small. This is great. We're done. I'll follow along with the textbook. If we divide both sides of this equation by dt, then on this side, we're talking about the mass of the rocket and the acceleration of the rocket, dv dt. So the force on the rocket, the thrust that the rocket experiences, is apparently equal to negative Vex dm dt. And remember, dm dt is the rate of change of the mass of the rocket. It's decreasing, so it's negative, which cancels this negative, and we actually do get a forward force accelerating the rocket. From where? From Newton's third law. From momentum conservation. We are throwing mass out the back. The mass is throwing us forward. There aren't any external forces to this system. The sum of the external forces was 0. So, and that we need that so that the momentum, it's the momentum conservation, it's Newton's third law that actually thrusts the rocket forward. Really cool. If we integrate let's start from here. I'll move the m to this side. I said I was going to. dv equals negative Vex dm over m. And if we integrate both sides from 0 to something, right, from v0 to v and from the associated m0 to m, then on this side we've got v minus v0. On this side, the minus Vex, we don't need to move it over. It's not a variable. It's just a constant. So it's just hanging out there. That gets us a natural log of m over m0. Now, if this is a rocket, we're expelling fuel. The actual mass we have is less than the mass we started with. So the natural log of a fraction less than 1 is going to be negative. We can change that if we put the minus sign, multiply that minus sign through, v equals v0 plus vex ln m0 over n. And these two equations are the rocket equations. And where do they come from? Momentum conservation. Okay. Cool. Next segment.